So here is the workflow for the impeller optimization, where the blade loading parameters are used to generate the blade shape in Turbo Design 1, and then the resulting performance parameters are fed into Turbo Design Optima, which basically applies the reactive response surface or the RRS algorithm to drive the solution towards the optimum design. So now a little bit about RRS. So there are usually two different approaches taken when it comes to design optimization algorithms. The first is a design of experiment based on space filling schemes such as Latin hypercube. And because the optimization is performed on a surrogate model, it is very fast, but then the Pareto front lacks accuracy for the same reason. On the other hand, we have direct optimization using genetic algorithms, which solves for every single design and renders a very accurate Pareto front, but then consumes a lot of computational time and resources in the process. But Optima uses a third approach called the reactive response surface, which takes from the best of these two methods and is one of the most advanced surrogate models available today. So basically, it starts from a small design matrix and then intelligently uses surrogate-based Pareto fronts to add additional points to the design matrix in areas of interest to the optimization. And then this leads to a highly accurate Pareto front, but only at 10% of the computational cost of direct optimization with the MOGA approach. And of course, we start by selecting the target case for optimization, which is the parametrically redesigned impeller, and specify the various settings for the RRS algorithm. And next, we specify the range of variation for the inputs, which are the streamwise loading parameters that are used to design the loading distribution as shown here. And in fact, in Optima, there is a machine learning based feature that can provide initial stage estimates, range estimates for these streamwise loading parameters, which helps to explore a large design space, but also avoids infeasible solutions. Now, since we have already identified the optimal leading edge sweep, exit hub radius, and stacking through our parametric study, these are not varied in this optimization. And then these are the constraints that are used. So we constrain the throat to confine the best efficiency point and the overall diffusion ratio to avoid flow separation, and also the leading edge bow ratio to limit the blade stress. And finally, for the optimization objectives, we want to minimize the total profile loss to increase the impeller efficiency, and at the same time, we want to maximize the minimum pressure in order to control cavitation. So in this way, we ensure that the blade integrity and suction behavior are not compromised in the process of improving its hydrodynamic performance. And this is what happens when the RRS optimization is run, and we can see these designs starting to appear on a scatter plot between the two objectives, the profile loss on the x-axis and the minimum pressure on the y-axis. And of course, this is a fast forward of the run, but even otherwise, it took only 5 minutes or so to complete on my office workstation. And so once the optimization completes, we can choose to see the Pareto front of optimum designs, from which we can pick and analyze any design of interest. And the target case, which was the parametrically redesigned impeller, actually sits here. And in this case, we have selected a design which has a much higher minimum pressure for the same profile loss. And so we use this design for further analysis and for comparison with the redesigned impeller. And in fact, this is what has changed as a result of the optimization. So compared to the redesigned impeller, the optimizer has recommended quite a complex streamwise loading, as it attempts to increase the minimum pressure while keeping the profile loss down. And CFD blade loading plots confirm that there is no risk of cavitation in this optimized impeller as well. And looking further into more results, it's interesting to see the effect on the TD1 parameters, where the increase in minimum pressure from optimization does not adversely impact the profile loss or the bow ratio. And then we run stage CFD with the optimized impeller, and what we find is that the design point stage efficiency rises further and is now almost 1 percentage point above the baseline pump. And the pump head has also advanced further and is now 15% higher than the baseline pump. And also the NPSH-R shows a further improvement and is now actually 0.6 meters below the baseline pump value. And it's again worth noting that the work distribution has not changed from the original even after this automatic optimization.